Okay, get ready, because today we're diving deep into the world of photonic space-time crystals.
Ooh, those are,
You sent over some research,
yeah.
and these materials sound incredible, like a whole new level of control over light.
And, that control could revolutionize so many technologies.
Yeah.
Like we're talking faster internet,
Wow.
more powerful lasers, even things like quantum computing could be impacted by this.
So let's unpack this a little bit.
Okay.
What makes these crystals, these photonic space-time crystals,
Yeah.
so special? I mean, the name alone
Just in the mouth.
sounds like something straight out of science fiction.
It does. It really does.
Right.
But the science behind it, it's real.
Okay.
These crystals are unique because their structure doesn't just vary in space like a typical crystal does.
Right.
It also changes periodically over time.
Okay.
So imagine like a choreographed dance, constantly shifting and changing, allowing it to interact with light in ways we've never seen before.
So it's not like the crystal itself is like traveling through time.
No, it's more like...
Its properties are evolving
Yeah.
over time
Yeah.
in this pattern.
Yeah. And this time variation is key to manipulating light in incredibly precise ways.
Okay.
For example, it allows for the modulation and amplification of light's spectral composition.
So essentially we can change the color and intensity of light passing through these crystals.
Yes, exactly.
I'm starting to see why this has everyone so excited.
Yeah.
But one thing I really got that caught my eye in the research was the concept of a band gap.
Right.
What is that?
The band gap.
And why is it so important in this context?
Yeah, so the band gap is a crucial parameter
Okay.
that essentially determines the conditions under which light can be amplified within the crystal.
Okay.
Think of it like a gate that only allows light with specific energies to pass through.
Okay.
The wider the band gap, the greater the range of light frequencies that can be amplified.
So a wider band.
Yeah, wider band.
More potential for
Yes.
manipulating and amplifying light.
Precisely.
And that's where things get interesting.
That's where it gets fun.
Right.
You see, previously,
Yeah.
achieving a wide band gap required really intense variations in a material's properties,
Okay.
like its refractive index.
Uh-huh.
But most materials have a limited range
Sure.
in which these properties can be changed.
So that sounds like a major roadblock.
It was a major roadblock.
Okay.
But the research you sent over highlights a groundbreaking new approach.
Yeah.
Scientists at the Karlsruhe Institute of Technology,
Yeah.
along with collaborators from other universities,
Okay.
have found a way to overcome this limitation by combining photonic time crystals
Right.
with a spatial structure, creating what they call photonic space-time crystals.
And how do they manage to do that?
Their innovation was to integrate these crystals with tiny silicon spheres.
Silicon spheres.
Yeah.
What role do they play in all of this?
These spheres are the key to unlocking a wider band gap.
Okay.
Think of them as tiny resonators that trap light,
Mhm.
allowing it to interact more intensely
Okay.
with the periodic changes happening within the material.
So they're like little holding cells
Ooh, I like...
for the light,
Yeah.
giving it more time to dance
Yeah.
with those time variations.
That's a great way to visualize it.
Go.
And this enhanced interaction is what leads to a dramatically wider band gap.
I'm curious.
Yeah.
What's so special about silicon in this context?
That's a great question.
Why not use some other material?
So silicon is an excellent material for this application for several reasons.
Yeah.
First, it's abundant and readily available,
Mhm.
which makes it practical from a manufacturing standpoint.
Okay, makes sense.
Second, we have a deep understanding of silicon and its properties,
Sure.
thanks to decades of research in the semiconductor industry.
Makes sense.
And finally, silicon exhibits unique optical properties that make it ideal for interacting with light in this specific way.
That makes sense. This is all starting to make sense, but I have to admit, my brain is still trying to
Wrap your head around it.
wrap itself around this concept of
Yeah.
these crystals existing in 4 dimensions.
Yeah.
How do we even begin to conceptualize that?
It is a mind-bending idea.
Right.
But let's break it down.
Okay.
A typical crystal, like a diamond, has a structure that repeats in 3 spatial dimensions.
Okay.
You can move up and down, left and right, forward and backward through its lattice.
Right, I get that.
Now, with a photonic time crystal,
Okay.
we're adding another dimension.
Yeah.
Time.
Time. Okay.
So not only does the structure repeat in space,
Right.
but it also changes periodically over time. It's like adding a 4th axis to our mental map.
So it's not that the crystal is physically moving through time,
No.
but rather that its structure is
It's more like
evolving over time.
exactly. And those changes occur in a predictable repeating pattern,
Okay.
which is what gives us such remarkable control over light.
Okay, I think I'm starting to grasp the concept.
Good.
But what does this wider band gap
Uh-huh.
actually mean in terms of real-world applications?
Yeah, that's the big question.
How does this translate into faster internet speeds or more powerful lasers?
That's where things get really exciting.
Okay.
Remember we talked about how the band gap determines the conditions under which light can be amplified?
Yeah.
Well, in these optimized systems with the silicon spheres,
Okay.
the band gap extends across nearly the entire momentum space.
Momentum space. Can you explain what that means?
Yeah, think of momentum space as a way to describe all the possible directions and speeds light can have within the crystal.
Okay.
The fact that the band gap now covers nearly this entire space means that light can be amplified regardless of its direction of propagation.
So it's like we've removed
Yeah,
the directional restrictions on light amplification.
exactly.
Wow.
And this breakthrough has profound implications for a wide range of technologies.
Like how?
Well, like,
Give me some.
concrete examples.
Well, for starters, think about fiber optic cables
Right.
that carry data across the globe.
Right.
By precisely controlling light amplification in these fibers, we can potentially transmit information much faster
Wow.
and more efficiently than ever before.
Okay.
This could lead to significantly faster internet speeds.
So we're talking about a potential internet revolution.
Potentially.
That's incredible. What about lasers?
Lasers.
How would this impact laser technology?
Lasers rely on the principle of stimulated emission,
Okay.
where light is amplified within a specific material.
Right.
The wider band gap achieved with these photonic space-time crystals could lead to the development of lasers that are more efficient, more powerful, and capable of operating at a wider range of frequencies.
Wow.
This opens up possibilities for advancements in fields like manufacturing, medicine, and even scientific research itself.
This is all really exciting stuff.
Yeah, it's really cool.
But before we get too carried away,
Yeah.
the potential...
Potential applications. I want to bring up a comment from Bahua Zhang
Oh, yeah.
that I found particularly thought-provoking.
Yeah.
They raised some fundamental questions about the very nature of these photonic space-time crystals.
And those questions are crucial.
Yes.
While we celebrate the technological advancements, it's equally important to grapple with the theoretical implications.
So they asked, are photonic space-time crystals two-dimensional, three-dimensional, or others?
Right.
And what is the space-time background of the photonic space-time crystals?
These are profound questions that challenge our understanding of dimensionality and the fabric of reality itself.
Yeah.
We'll definitely need to explore these deeper implications further in our deep dive.
Agreed. But before we delve into
those philosophical depths.
Decks, let's take a closer look at the specific innovations
that
led to this breakthrough. You mentioned the silicon spheres, but I'm curious to learn more about how they actually work to create these wider band gaps.
Yeah. Absolutely. To understand that, we need to delve a bit deeper into the world of photonics and the fascinating ways light interacts with matter.
Let's do it. I'm ready to dive deeper.
Let's do it.
Into the details.
All right.
We've laid the groundwork, but I'm really eager to understand the mechanics of these silicon spheres.
Yeah.
How do they actually create this wider band gap that unlocks all these amazing possibilities?
Let's dive into the fascinating realm of photonics.
Okay.
When light encounters matter, it doesn't just pass through unimpeded.
Right.
It interacts with the atoms and electrons in the material. And this interaction can alter the properties of the light itself.
So the light isn't just bouncing off these silicon spheres?
No.
Like tiny billiard balls?
No, not at all. There's something more complex.
Happening at the atomic level.
Precisely. In the case of these photonic space-time crystals, the silicon spheres act as tiny optical cavities or resonators. When light enters these spheres, it gets trapped inside for a short period, bouncing back and forth between the internal surfaces.
So they're like miniature light traps.
That's a great way to think about it.
Okay.
And because the properties of the surrounding crystal are changing periodically over time, the trapped light interacts much more strongly with those changes.
Okay.
It's like giving the light more opportunities to feel the temporal variations of the crystal.
This is where my brain starts to hurt a little.
I know, it's a lot.
How does this intensified interaction actually translate into a wider band gap?
How the energy of the light aligns with the allowed energy levels within the crystal structure.
Okay.
Think of it like a musical instrument. You can only produce certain notes based on the physical properties of the instrument.
Okay, so I'm following you.
Similarly, the crystal structure only allows certain frequencies of light to be amplified.
Okay.
The band gap represents the range of frequencies that are allowed or forbidden.
Right.
When light gets trapped inside the silicon spheres and interacts more intensely with the time-varying properties of the crystal, it essentially samples a wider range of those allowed and forbidden frequencies.
So the spheres are helping the light explore a wider range of the crystal's energy landscape.
That's a great way to put it.
Okay.
And as a result, the band gap widens, allowing for amplification of a much broader spectrum of light frequencies.
That makes sense.
Yeah.
So we've gone from a limited band gap that only allowed for amplification in certain directions to a wider band gap that works.
To a wider one.
Regardless of the direction of light propagation.
Exactly. That's a big deal.
That's a game changer for optics and photonics.
It is indeed. It opens up a whole new world of possibilities for controlling and manipulating light.
Okay, but before we dive into those possibilities, I want to circle back to that intriguing comment from Baohua Zhang.
That's a good point,
They raise some fundamental questions about the dimensionality of these photonic space-time crystals.
That's where things get really interesting from a theoretical perspective. Zhang's questions challenge us to think deeply about the nature of these crystals and how they relate to our understanding of space and time.
Well, they specifically asked if these crystals are two-dimensional, three-dimensional, or something else entirely.
Or something else,
What do you make of that question?
It's a question that goes to the heart of how we define dimensionality. On one hand, we can think of these crystals as three-dimensional structures that are changing over time. The silicon spheres are physically arranged in space, and the properties of the crystal are evolving temporally.
So that would seem to suggest three dimensions.
Yes, but it's not quite that simple. The fact that the temporal variations are so precisely controlled and integral to the crystal's functionality adds a whole new layer of complexity. Some argue that the periodic changes over time effectively constitute a fourth dimension, blurring the lines between space and time.
My brain is officially starting to melt.
It's a lot to take in, I know.
So we have this complex interplay of spatial and temporal dimensions, and it's not entirely clear how to categorize them.
It's a really interesting question.
What about Zhang's second question about the space-time background of these crystals?
That's a question that delves into the very fabric of reality itself. It's asking us to consider what underlying framework governs the behavior of these crystals and how they interact with the fundamental forces of the universe.
That's getting pretty deep.
It is. And there's no easy answer. Some physicists believe that these crystals could provide insights into the nature of space-time itself, potentially revealing new connections between general relativity and quantum mechanics.
So this research isn't just about building cool gadgets.
No, it's much bigger than that.
It's about pushing the boundaries.
It's about pushing the boundaries
of our understanding of the universe.
Absolutely. And that's what makes this field so exciting. It's at the intersection of cutting-edge technology and fundamental scientific inquiry.
All right, I think we've explored the conceptual and theoretical aspects of these photonic space-time crystals pretty thoroughly.
I think so.
Now I want to shift gears and talk about the practical implications. What kind of real-world applications
are we
talking about? And what impact could they have on our lives?
That's where the rubber meets the road, so to speak. And the potential applications are vast, far-reaching.
Give you some more examples. What else can we?
We've already touched on faster internet speeds and more powerful lasers. But those are just the tip of the iceberg.
Okay, so what else?
Well, let's start with computing. Imagine optical computers that harness the speed and efficiency of light to perform calculations at speeds far beyond what's possible with traditional electronics.
Optical computers, it sounds like something out of Star Trek.
It does, doesn't it?
Right.
But it's a technology that's actively being pursued.
Why?
And photonic space-time crystals could play a key role in making it a reality.
Okay.
These crystals could be used to create optical transistors, logic gates, and other components that operate at the speed of light, potentially leading to a revolution in computing power.
That's mind-blowing.
It is. It really is.
What about other areas like medicine or energy?
The possibilities are truly exciting. In medicine, these crystals could revolutionize imaging techniques, allowing for higher resolution scans with lower radiation exposure.
Okay.
They could also be used to develop new types of optical sensors for detecting diseases at an earlier stage.
So we're talking about the potential to diagnose and treat diseases more effectively.
Yeah.
That's incredible.
Yeah, it really is.
And in the realm of energy, these crystals could lead to advancements in solar energy harvesting, making solar panels more efficient at converting sunlight into electricity.
Exactly.
They could also play a role in developing new types of optical energy storage devices.
Yeah, lots of possibilities.
Wow, the potential applications seem almost limitless.
They do.
It sounds like this technology could have a profound impact on nearly every aspect of our lives.
I think you're right. And the most exciting thing is that we're still just scratching the surface of what's possible as research progresses. And we gain a deeper understanding of these crystals. We can expect to see even more groundbreaking applications emerge.
This is definitely one of those topics I'm going to need to revisit as new discoveries come out.
Yeah, for sure.
It feels like we're on the cusp of a major technological revolution.
I agree. And the best part is that this revolution is rooted in fundamental scientific inquiry, pushing the boundaries of our understanding of the universe.
Well, I think we've covered a lot of ground today.
Yeah, we have.
From the intricate details of silicon spheres to the philosophical implications of dimensionality, exploring the potential of this revolutionary technology to reshape our world.
It's an exciting time.
But before we wrap up, I want to bring it back to the listener.
Okay.
Leave them with some key takeaways and food for thought.
That's a great idea. It's important to distill all this information into something that our listener can walk away with and contemplate further.
So let's synthesize what we've learned and provide our listener with a clear understanding of what these photonic space-time crystals are, why they're so important, and what the future might hold for this revolutionary technology.
The future is bright.
So for our listener who's been following along on this deep dive into photonic space-time crystals, let's bring it all together.
Okay.
What are the key takeaways they should remember?
Well, the biggest one is this incredible leap forward in our ability to control light.
Okay.
We've moved from a place where amplifying light was restricted by direction to a world where these crystals can amplify light regardless of which way it's traveling.
Yeah.
It's like we've unlocked a new dimension of control.
And that control stems from the unique structure of these crystals. Right? It's not just about their spatial arrangement, but also how their properties change over time.
Exactly. It's that four-dimensional aspect that makes them so revolutionary.
Right.
The silicon spheres play a crucial role, acting like tiny resonators that intensify the interaction between light and the time-varying crystal structure, leading to that wider band gap that makes all the difference.
We've talked about a lot of potential applications.
We have.
From faster internet speeds and more powerful lasers to advancements in computing, medicine, and energy. It feels like this technology has the potential to touch nearly every aspect of our lives.
It does, and I think that's what makes this field so captivating. It's not just about incremental improvements. It's about fundamentally changing the way we interact with light and harnessing its power in ways we never thought possible.
But as we've discussed, there are also some profound theoretical questions to consider. Bao Huizhang's comment about dimensionality and the space-time background of these crystals really pushed us to think beyond the technological applications and grapple with the deeper implications.
Absolutely. While the technological advancements are exciting, it's crucial to remember that they're built upon a foundation of scientific inquiry that seeks to understand the fundamental nature of reality. These crystals might offer us a glimpse into the very fabric of space and time, potentially revealing new connections between general relativity and quantum mechanics.
It's almost like we've stumbled upon a doorway.
It is. It really is.
To a whole new realm of understanding, and we're just beginning to explore what lies beyond.
That's a great analogy, and it reminds me of that famous quote from Arthur C. Clarke.
Oh, yeah.
Any sufficiently advanced technology is indistinguishable from magic.
Oh, I love that quote.
Yeah.
And in a way, these photonic space-time crystals do feel almost magical.
Yeah.
In their ability to manipulate light.
They do, don't they? But the magic lies not in some supernatural force.
Right.
But in the beauty and elegance of the underlying science.
So for our listener who's now brimming with curiosity and eager to learn more, where would you direct them? What are some resources they can explore? Or key terms they can search for to delve deeper into this fascinating field?
I'd recommend starting with the research papers you send over,
Okay.
as they provide a solid foundation and highlight the key findings from the Karlsruhe Institute of Technology and their collaborators. From there, exploring resources on photonics, metamaterials, and optical physics would be a great next step.
And of course, keeping an eye on reputable science news outlets and journals is always a good way to stay up to date on the latest breakthroughs.
Absolutely. This is a field that's moving rapidly, so there's always something new and exciting to discover.
Well, I think we've given our listener a lot to think about today.
I think so.
We've journeyed from the intricate workings of silicon spheres to the philosophical depths of dimensionality.
It's been a journey.
Exploring the potential of this revolutionary technology to reshape our world.
It's really fascinating stuff.
And who knows what incredible applications we'll be discussing in our next deep dive.
I don't know, but I'm excited to find out.
The future of photonics is bright indeed.
It is.
On that note, we encourage our listener to keep exploring, stay curious, and join us again for another deep dive into the fascinating world of science and technology.